Bismillahirrahmanirrahim. I am Abid Babul, your chemistry teacher for GSCH 101. This is the last lesson, last video for your this course. It is about the module 9 and the third lesson of the module 9. In this video we'll learn about the weak acid and weak base and how to calculate their pH and pOH, and at the end also we will learn what are the buffer solutions and how to calculate their pH. So now let's start our lesson. Electrolytes are the chemical through which the current can pass. Strong electrolytes are those electrolytes through which the current can pass easily, and weak electrolytes are those electrolytes through which the current cannot pass easily. It is like solid state. Like silver and gold, the current can pass easily, so they are called good conductors. And aluminium or magnesium, the current cannot pass easily, so they are called bad conductors. So in chemistry, the chemical, if you add in the water and if it pass the electric current, then it is called strong electrolyte. And the chemical, when you dissolve in water, if it do not allow the current to pass through it, or the less amount of current pass through it, then it is called weak electrolyte. What is the reason? The reason is that some chemicals, when you dissolve in the water, they are 100% dissociate into ions, cations and anions. This formation of cation and anion is called dissociation into positive and negative ion. If it is 100%, then more charge will be there, more ions will be there, current will pass easily, and it will call strong electrolyte. Opposite of it, some chemicals like this acetic acid, you dissolve in water, it will not be 100% dissociate, it might be 1% to 4% dissociation. So it might be 4% maximum dissociation. So it will not produce more ions, the cation and anions. So it is not good electrolyte. More current cannot pass, so it will call weak electrolyte, and it will be a weak acid. So if the strong electrolyte, it is strong acid. If the weak electrolyte, it is weak acid. If the strong electrolyte, it will be strong base. If it is weak electrolyte, it will be weak base. So strength of the acid and the base depend on the strength of the electrolytes. That's if how much percentage it dissociates. So this thing now we have to understand by the example. This is the examples of strong acids. All these acids, hydrochloric acid, nitric acid, chloric acid and sulfuric acid, when they are put in the water, all of them dissociate 100%. 100% it will go into dissociation, positive and negative ion will form. So these are all 100% dissociation, so they are strong electrolyte and the strong acid. Strong electrolytes are strong acid. Weak acid like hydrofluoric acid, nitrous acid and water are weak acid. Water is both acid and base. Water both acid and base, but it will be weak acid and weak base. Why? Because they do not dissociate 100%, so this will be weak electrolyte. Weak electrolytes are weak acid. The strong base, sodium hydroxide, potassium hydroxide, barium hydroxide, when they put in the water, it will 100% dissociate into the cation and anion, so dissociation is 100%. So a strong electrolyte are strong base also. So strength of the acid and base depend on the dissociation. 100% dissociate, strong. Not 100% dissociate, weak. Okay, more example here. Weak bases are weak electrolyte. These are the weak bases here. When they dissolve in the water, they do not dissociate 100%. They are weak base. So now this some conclusion here. First one, this one, hydronium ion, or you say hydrogen ion also in simple form. If it is the strongest acid, okay, and hydroxyl ion is the strongest base here. This is a common thing. And this conjugated base of the strong acid has no measurable strength. This you can understand here. So this is the example of acid and their conjugated base. In this list of the acid, the strength of the acid increases upward here in this case. Okay, so perchloric acid, this here perchloric acid, the strongest acid here, and but the conjugated base of this acid will be weak. The strength of the conjugated base goes downwards as the strength of the acid goes upward, inversely proportional, you can say. So more stronger the acid, the conjugated base of that acid will be weaker. If the acid is weak, and their conjugated base will be strong, OH is strong. So this inverse. So this is same thing in another diagram, another picture. The strength of the acid increases like this, and the strength of the base decreases this way. The red color shows the acid, and the blue color shows the base. So it means the strength of the acid increases, the strength of the conjugated base decreases. Here same relationship. Here this another example. In this diagram is taking hydrochloric acid. Hydrochloric acid is strong acid, and the system there is no remaining of HCl. All the HCl is converted into H and Cl. This is Cl, this is Cl, and H is converted into hydronium ion, H3O positive. So 100% HCl is finished here. But in case of HF, so it is not 100% dissociate. This is HF remaining here, this is HF remaining here. You can see these signs here, what is the HF and what is the Cl and what is the F. So this will show you this is 100% dissociate hydrochloric acid, but this is not 100% dissociate, so it is weak acid, and this is strong acid. By the diagram and dissociation, it shows the dissociation of the molecule in the diagrammatic way. Now, how to know which one is the weak acid and which one is the strong acid mathematically? So we have to make an equation, that is equilibrium expression here. This equation comes from a general equation. We take a general equation, and then if in this case this is the acid or this is the base, but this is pure water, so we remove this pure water from here and write the chemical equilibrium expression. So this will give you the chemical equilibrium constant for the acid will be equal to the product upon reactant. The product is positive and negative ion, and the reactant will be the acid itself, and this equation will give you the value of Ka, and by looking at the value of Ka we can tell this is strong or weak. If the Ka is a big value, acid will be strong, strength will be high. If the Ka is small, the acid will be weak, directly proportional. So Ka is called the acid ionization constant. A means this acid. So by looking at the value of Ka, if the Ka value is big, acid is strong. If the Ka value is small, acid is weak. We will see this by the example also. Now we talk about the base also. In the base system, again we take the equation and take the base, put in the water, so dissociate into ions, positive and negative. This water is a pure water, so we remove this from the equation and we get this equilibrium expression here, and this is the equilibrium constant for the base, and these values will give the constant Kb. If the Kb is big, as base is strong. If the Kb is small, the base is weak. Same thing here. So this thing we will see in the table how. So this is the Ka equilibrium constant for the acid. These are the example of the acids, and we see this value is bigger than this value is small, so strength of the acid will increase upward because this Ka is bigger this way, okay, and the conjugated base here is the same. This is Kb for this conjugated base, inversely proportional here. This is also, but you can see here, but this Ka value is clear here, that Ka value is decreasing, so strength of the acid is decreasing. If the Ka value is high, this is high here, so this is stronger acid among the list of the acid, and this is low value, so this will be the weak acid. Similarly, in case of base, is giving you the value of Kb here, so this is the high value, so this base is stronger, and this is the small kb, so this base will be weak. So again the strength of the acid is higher towards the upward side, and it is low at the lower bottom here. This is the smallest value, so this is the weakest base among the weak bases. So now we can solve the problem to check the acid and the base, the Ka, for about the weak acid and the weak base. So he's asking you the pH of this 0.1 m solution of formic acid is 2.39. so this is pH, and the concentration of the acid is 0.1, and he's asking you the Ka. So how to calculate the Ka? So to calculate the Ka, you need the concentration of the reactant and the product, but you don't have the concentration of hydrogen ion. Let me write the equation here for this formic acid. So this is very easy. So HCOOH, formic acid, when it dissociate, you can say the water, but you have to cancel the water because water is pure. Then you can remove this water also. So directly you can say this will be dissociated into HCOO negative formate ion plus hydrogen ion. Okay, hydrogen ion. So at the beginning, you can say here we have to know the value of this hydrogen ion. This we don't know, but the pH is given. So we calculate the pH first, hydrogen ion concentration. So as you know, this pH is equal to negative log of hydrogen ion. So make the reverse of this equation. Hydrogen ion is equal to shift log minus pH. So you can say shift log minus 2.39. So hydrogen ion will be equal to 4.1 minus 3. 4.1 to 10 to the power minus 3 molarity. This is hydrogen ion concentration. You can put here. Okay, now see, when the time was 0, means in the beginning it was 0.1 molar. This water we are not considering here, is pure, and this was 0, formate ion was 0, and hydrogen ion was also 0 in the beginning. After that passage of time, the equilibrium comes, and we can say at equilibrium it will be 0.1 minus how much hydrogen goes from here, that is this hydrogen will go from here, consume. So we can say minus 4.1 into 10 to the power minus 3, and this formate ion will be also equal to 4.1 into 10 to the power minus 3 molar concentration, and this will be also 4.1 into 10 to the power minus 3 molarity, because this is format is 1, this is hydrogen is also 1, so they both will be equal. And now we can write the equation for the Ka, because we have all the 3 concentration, 2 product and 1 reactant. So Ka is equal to product upon reactant. The product is formate ion HCOO negative and hydrogen ion positive, and the formic acid is the reactant, it will go down, HCOOH. Okay, all powers are 1 because this is 1, this is 1, so there is no square root 3, so we just write the values here. So this is 4.1 power minus 3, 4.1 power minus 3. Hydrogen ion is also 4.1 minus 3. You can also write the square here. So 4.1 into 10 raised to the power minus 3, both are same. And this will be 0.1, yes, minus 4.1 into 10 raised to the power minus 3. So this will give you the answer. Answer is 1.8. Yeah, this will be answer will be equal to 1.8 into 10 raised to the power minus 4. So this is the answer. Similarly, in the practice exercise, he is giving you this the pH, okay, and he is asking you same the Ka of this acid, monoprotic. Monoprotic means the equation is balanced. Same, monoprotic means it have one hydrogen ion to release, so this will be 1 here. This is called monoprotic. So the same equation and same thing is there. So we write some, this is the acid, we say this is the acid. Suppose you don't know here the name of the acid, so you just write the acid and you dissociate into some negative ion, and then you can say H plus ion, the positive ion, okay. So similarly, you have to first check the hydrogen ion, how much is here. So we say here hydrogen ion is equal to use this time other equation, 10 raised to the power minus pH, okay, and then we will say here is equal to 10 raised to the power minus, how much is the pH, 3.44. so 3.44. so that will give you the answer. How much is the answer? Let me check this mathematics. 3.6 minus 4. So 3.6 into 10 raised to the power minus 4 molarity. This is the concentration of the hydrogen ion, okay, H plus ion, and also it will be the negative ion. Both are one, same. This is 1 and this is 1, so both will be equal. So now let's start here. When the time was 0, means initially this was 0.06 molar, and this was not there, this was also not there in the initial concentration. After time when the equilibrium comes, and we can say at equilibrium this was 0.06, and some consumption is there. How much consumption is there? That is our hydrogen ion concentration. This is consumed in the from the reactant, so minus, because this is consumed, 3.6 into 10 raised to the power minus 4. The negative ion will be also 3.6 into 10 raised to the power minus 4 molarity, and hydrogen ion is also same, 3.6 into 10 raised to the power minus 4 molarity. Now we can write the Ka. So dissociation constant of the acid is equal to product upon reactant. The same beside the product, this is a negative ion and the positive ion, and this is the acid here. We don't know the name of the acid, so we write just acid simply. So this will be 3.6 into 10 raised to the power minus 4 multiplied by 3.6 into 10 raised to the power minus 4 and divide by 0.06 minus 3.6 into 10 raised to the power minus 4. So the answer will be equal to here 2.2 minus 6. So this will be 2.2 into 10 raised to the power minus 6. This is the answer. Okay. Now this one here, 15.10. what is the pH of ammonia? What is the pH of ammonia here? So here we have to do the same thing. He is asking you, Kb is given, and he is asking the pH of ammonia. So first we have to calculate the OH ion concentration. To calculate the OH ion concentration, we have to write the equation of this ammonia. Okay. So we say this is ammonia NH3. We put in the pure water H2O. So this will be dissociated into NH4 positive ammonium ion and the hydroxyl ion, this one. Okay, because this is pure water, we don't consider it here in the calculation. So again we say same thing, time is equal to 0, means initially when the time was 0, the concentration was 0.4, and this was 0, this was also 0. After the time, means at equilibrium, this was 0.4 minus something change, we don't know, because the pH is not, we are going to calculate the pH, so we don't know how much dissociate. If we don't know things, so we call it X. Okay, and this will be also X, because we don't know how much it dissociate, we don't know, so it will be X. So we write the equation for equilibrium. So Kb is equal to, now this will be ammonium ion NH4 positive multiplied by hydroxyl ion OH negative divided by the base. The base is ammonia here, NH3, because this quotient for the base. And then we can say here this will be equal to, this is both equal, this ammonia is X, ammonium is X, and hydroxide is also X, so this will become X square, you can say, and the ammonia is 0.4 minus X. Okay, so now here this X, or we write this equation, we write the value of Kb. So let us solve this here. How much is the Kb? This equation Kb here, Kb is 1.8 into 10 to the power minus 5, this is given in the question, is equal to X square, okay, divided by 0.4 minus X. This X is very small, so we can neglect it. Okay, make it 0, so our equation will become easy. Otherwise we have to go for long calculation. So if we suppose this X is very small, so this equation become very easy for us. Otherwise we have to use quadratic equation, which we don't want to go for long procedure. So now we just removing this X and cross multiply, so this X square will be X square, sorry, this is X square is equal to 1.8 into 10 to the power minus 5 multiplied by 0.4. If you remove the square and put the X, so this will be under root 1.8 into 10 to the power minus 5 multiplied by 0.4. So that will be equal to how much? That will be equal to 2.7 minus 3. 2.7 into 10 to the power minus 3 molarity, and this is the OH concentration. OH concentration. Now we change it, this OH, into POH. So we say POH is equal to negative log OH negative. So this will be equal to negative log 2.7 into 10 raised to the power minus 3. So that will be equal to 2.57. 2.57. This is pOH. So how to calculate the pH? So we say pH plus pOH is equal to 14, because our question is pH, not pOH. So pH is plus pOH is equal to 14. So we can say like this, 14 minus pOH will be equal to how much? 14 minus 2.57. 2.57 will be equal to 11.43. 11.3. Answer is there, 11.43. So this is the answer. Similarly, we have calculated the pH. This is the same question. Concentration is 0.2 methylamine. Okay, and the Kb is given here. So we solve this also same methylamine. I will write this is methylamine as Ma. Okay, methylamine is a base, and just we say dissociate into some methylamine and negative, and sorry, this is negative. Let me delete this. Okay, you understand this is methylamine negative, and the hydroxyline plus, because this is base, because we are dealing with the base, so this will be OH here, OH negative. This will indicate this is base. Okay, so same, the time is 0, so this will be concentration is 0.26, 0.26 molar, and negative ion 0. This is positive, sorry, this is positive and this is negative, so this will be also 0. At the equilibrium, this will be 0.26 minus x, because we don't know here, and this is x, and this is also x, and this is also x. So we write this equilibrium expression here. It is Kb. Kb is equal to same, this is x square. I'll write this x square upon 0.26 minus x. Now I'll solve here. Okay, so we write the value of Kb. Kb is 4.4. 4.4 into 10 raised to the power minus 4 is equal to x square upon 0.26 minus x. So this x is very small, so we can remove it. So this equation will become like this: x square is equal to 4.4 into 10 raised to the power minus 4 multiplied by 0.26. Okay, if you remove the square here from the x, so it will be under root. Same value, 4.4 into 10 raised to the power minus 4 multiplied by 0.26. So x will be equal to what? X will be equal to 0.0106. 0.0106. This is molarity, and this is equal to OH. Equal to OH negative. Okay. So now we can say here this is OH. So we calculate the pOH. Yes, we calculate the pOH. pOH is equal to negative log OH concentration. So negative log 0.0106. So pOH will be equal to 1.97. 1.97. So now then we convert into pH. So pH plus pOH is equal to 14, and we can say this is pH is equal to 14 minus pOH. So 14 minus 1.97 will be equal to our answer 12.03. Okay, now then another topic is the common ion effect. Common ion effect is the when a chemical, suppose this is the sodium acetate, you put in the water and this dissociate into sodium and the acetate ion, okay, and then you put the acetic acid in it. So two chemicals you are combining. One is the salt, the strong electrolyte from the weak acid, another is the itself is a weak acid, and this will dissociate into hydrogen ion and the acetate ion. So these two common ions are common, same, so it's called common ion. So when you mix two chemicals and the two ions produced are common, then it is called common ion effect, and this will become a buffer. So when the common ion effect is the shift in the equilibrium caused by the addition of the compound having an ion common with the dissolved substance. So this shift will make it a buffer, and this will become a buffer solution. So what chemicals we use? One is the salt. This salt comes from the weak acid, and because it's coming from a weak acid, so it will be strong electrolyte, and itself is the weak acid is there, that is acetic acid. Vinegar, in English we call it vinegar. Acetic acid is a weak acid, and the salt of the this acetic acid will be the strong electrolyte. If you combine these two chemical, it will give you common ion, and this mixture will be called buffer. So common ion is the common ion effect is the shift in the equilibrium when you combine two chemicals, weak acid with a strong corresponding strong electrolyte, okay, or the weak base with a corresponding strong electrolyte. So this combination will call buffer. Buffer is a special chemical which resists in the change in the pH upon addition of the small acid or small bases. It is a special mixture of the same, this is strong electrolyte and the weak acid, so this is called buffer. In this mixture, if you put little bit acid or the base, the pH will not change. So if the pH is not changing, then it becomes a buffer, and that's special combination. This buffer solution is used in the body, in the industry, to keep the pH same. If you want to keep the pH same, in the medicine also they use it to keep the pH same, and in the industry also, if you want to keep the pH same, use the buffer solutions. And buffer solutions are the combination of weak acid or base with their corresponding strong electrolyte, means salt. Okay, and then when you make the buffer, you need to calculate the pH. To calculate the pH, this is a simple equation. That equation is called Henderson-Hasselbalch equation. So Henderson-Hasselbalch equation is used to calculate the pH of the buffer solution. So buffer solution contains two chemicals. So one is the salt, another is the acid. So we can use this equation to calculate the pH of the buffer solution. So we go to this equation. Here I will not solve this part A because we already solved in the previous example. We solved this with other name, with other numbers, so you can solve yourself and check the answer, it is same. So I will not give the time in this video, you have to solve yourself. But the part B is the new thing, and that is for the buffer. So it's asking you calculate the pH of the solution containing both the things, means acid and their respective salt. Okay, so 1 minute, let me see this thing here? Yes. So we will write this equation here, the Hasselbalch equation, Henderson-Hasselbalch equation. This one, pH is equal to pK plus log salt upon acid. This pK means you have to log negative log of Ka. P means negative log. I told you in the previous, this is here given also here. pK means negative log of Ka. Okay, so we will write this equation here. pH is equal to pKa plus log salt upon acid or base. In this equation it is acid. Okay, and we open up this pK. pK is negative log, so we again write this equation. pH is equal to negative log Ka plus log salt upon acid. So we say here the negative log K is how much? K is 1.8 minus 5 plus, I will continue here, log, and then we say the salt upon acid. Salt is, you know, this is the salt. When you see the sodium, means it is salt, so 0.3, 0.3, and the acid is this one, CH3COH, acetic acid is 0.2, 0.2. You have to use the calculator and solve this separately. First take out the, first find out this negative log of this, then find out the value of this one plus log salt upon acid. So two parts solve separately and then make the total. Your answer will be here 4.92. You have to use the calculator and check the answer yourself. Okay, so now we go to this practice here. What is the pH? Same, this pH for the solution containing 0.3 m. This is the acid and this is the salt, and compare your result with the pH of the acetic acid. This is compare means of this formic acid, means in some this same question you calculate the pH again, but we will not compare anything. We will just calculate the pH to use this Hasselbalch this is equation. So we again write this equation, and I write this pH is equal to, we say, negative log Ka plus log salt upon acid. This is actually two part. First part you have to calculate only with the this formic acid. Only with the formic acid calculate the pH. That we have learned in the previous questions, so we are not repeating it again. So only this, now we will calculate only the pH by this equation. So we say negative log Ka is how much here? Ka is not given this equation, but I'll give you the Ka. The Ka is here 7.4 minus 3. 1 minute. Yeah, 1.7 minus 4. Ka is 1.7 minus 4. It will be given in the question. You have to see the table. 1.7 into 10 raised to the power minus 4. This is constant. Must be given in the question here, but he will tell you that go to see, check in the table in the book. From the table we find it, so no problem. Plus log salt is how much? Salt is 0.52, 0.52, and acid is here 0.3. 2.3. So this is two part. First you calculate this one. Okay, first you calculate it. You can do directly if you are expert to use the calculator, and the other part you calculate this one. Better to be safe to get the exact answer, and then make the total, make the plus. So your answer will be 2.15. Okay. So this is the end of the module number 9. I hope these videos are making your learning easy